This is the fourth lecture in a series of lectures covering first-order circuits involving inductors and capacitors. And in this lecture we want to talk about combining our knowledge of network reduction techniques with what we've learned so far regarding the solution to a first-order circuit. So what we've dealt with pretty much to date has been the basic RC circuit, which would be, a single loop involving a resistor and a capacitor and maybe a voltage source, and the basic RL, which we initially saw as or considered a parallel combination with a current source. We then also worked an example where we had a voltage source driving an RL in series. Okay, and I think you could at this point expand an RC, or consider another RC case where you might have a current source maybe with a parallel RC, right? You can do source transformation on this, right? And then you're back to a series circuit. But we've dealt with pretty simple circuits to date. So these kind of things we've looked at. Now we want to look at a circuit that's a little more involved and see if we can find the solution. So here's the circuit we're going to look at. Okay, we have a voltage source, Vs, which we'll say is equal to 6 volts. We have a 12 ohm resistor and a 6 ohm resistor and a 2 ohm resistor, and we have a 30 millihenry inductor. Okay, and what we want to know is we're looking for the current going through the 12 ohm resistor. Okay, so given that IL at time 0 is equal to, we'll say I naught, so we'll make it more general than I was going to pick 0, but we'll pick I naught. Find I12 of t. Okay, and we want the complete response. So the approach will be as follows. We are going to Thevenize the network that connects to L. Okay, L1. Say to L1. All right. To solve the RL circuit involving the Thevenin network. And when I mean solve is we'll get the complete response IL of t. Then we will return to the original circuit and express I12 in terms of IL of t and Vs. So this goes back to, I believe, the first lecture where we actually found that the response of a circuit, any branch current or node voltage, could be expressed as a weighted sum of all the independent sources and all of the energy storage states in the system. So that's what we're going to actually leverage off of here. Okay, so let's Thevenize the circuit. So what we notice here is that I can draw a dotted line here to separate IL. And we're going to Thevenize this. Okay. So let me redraw the network. So what we'll do is we'll look for our Thevenin. As I look at this, I think, okay, I think what will be easiest is to find our Thevenin and to find the V open circuit. So V open circuit is going to be the voltage here. V Thevenin is equal to V open circuit. When there's nothing connected to this network, we're not pulling any current. All right, and this is pretty easy to express. This is going to be, by inspection, I can see this is a voltage division of the Vs voltage across the 6 and 12 ohms. The 2 ohms does not enter into it because there's no current flowing through it. So we'll have 12 over 12 plus 6 times Vs, which we can say is 2 over 2 plus 1 Vs, or 2/3 of Vs, which is 4 volts, since Vs is 6 volts. Okay, and then our Thevenin is going to be equal to the resistance that we see looking in when we turn off the independent voltage source. So we'll see 2 ohms plus the parallel combination of 6 and 12 ohms. So this is 2 plus 6 times 1 in parallel with 2, and that will be 2 plus 6 times 2/3, or 4, so the Thevenin resistance is 6 ohms. So now we have our Thevenin network. It's going to be a 4-volt source, or I should say more generally 2/3 Vs, and a 6 ohm resistor. Okay? So that was one. Now we're going to connect our inductor back in here. Okay, so we'll connect the inductor, and we're going to solve for IL. Okay, so we already have found the solution to this circuit, and so I'm actually going to skip going through the lengthy process of solving this. I would refer you back to the previous lecture, or the lecture before that. The previous lecture, actually, lecture 3. All right, and instead I'm gonna write this by inspection. Okay, and let me show you how I'm going to do this. When I look at this circuit, I think, okay, what will the steady state current be? At some point when the current is no longer changing in time, and I expect it's not going to change any longer in time at some point, maybe at time infinity, because I'm driving the circuit with a constant voltage source, a constant source. So at that point, di dt is going to be 0. So at t equal infinity, sorry for that interruption. Now, at time t equal infinity, we say that the current is no longer changing in time. So we'll say that dIL dt is equal to 0, which means that VL, which is L di dt, is going to be equal to 0. And so therefore, the current IL, the particular response, okay, the steady state response, is then going to be just 2/3 of Vs, our voltage source, right, our Thevenin voltage source, divided by 6 ohms. Okay, so that'll be Vs over 9 ohms. Okay, and then the other thing that we can do by inspection is that we know that the response is going to, any change in state is going to be an exponential response. So the only thing we really need to know is to find the time constant. So find the time constant, tau. And we have solved this before. For an LR circuit, it's going to be the net resistance times, it's going to be the net inductance, L, divided by the net resistance, which we found the net resistance. It's this Thevenin equivalent. Right, so when you're trying to find the Thevenin or the time constant in an RL circuit, and you have multiple resistors, you want to go look at, you kind of position yourself as the inductor, and you say, all right, if I trace my way from one of my terminals through the circuit, through the resistors, and back to my other terminal, what resistors do I go through, and how do I go through them? Are they in series and parallel? And you basically come up with that effective or equivalent resistance. And you do that with the independent sources turned off. Well, we've already done that here because we found the Thevenin resistance. So it's just 6 ohms. So we have 30 millihenry divided by 6 ohms. So that gives us 5 milliseconds. Okay? So now I can write my response. I know that it's going to start at some I naught, and it's going to go up or go down depending on where I naught is relative to the steady state to Vs over 9 ohms. That's my steady state value. And it's going to move in an exponential manner with the tau equal to 5 milliseconds. So now I need to just write an expression for that. Okay, so we have IL of t is going to be equal to, I'll write the steady state response is this Vs over 9 ohms plus something that starts out at let's see, IO minus Vs over 9 ohms, and then it decays away. Okay, so I've picked this. I'm using the same form as what we found in lecture 3. Okay, so I'm not just making this up, but I can formulate this just by looking at the graph that I plotted, because if I know at time infinity I want this result here, so this is the steady state, and I know that at time 0 I want the current to be I naught, then the quantity right here that I'm going to scale the exponential by is going to be I naught, the initial condition, minus the steady state, so that I get a cancellation of the steady state when I'm at time 0. When you're at time 0, the exponential is equal to 1, right, at time equals 0. So that works out well. Okay, so this is our response for the current, right? And now we want to go back and find, return to the original circuit and express I12 in terms of IL and Vs. So notice that in the circuit we've been working with, there is no I12, right? Because I did a Thevenin. So there's no I12 in the Thevenin circuit. So we have to go back to our circuit up above here. And this here is I12, right? This current here is IL, which is what we just found. So now what we can do is we can do this several ways. We can do a superposition, which is I think what I'm going to do. Let me redraw this just to be clear about this. Find I12 of t. Okay, so we have the 12 ohms. We have the 6 ohms and our Vs, and then we have IL. Now I could actually draw in a current source if I wanted to. I mean, that's really what I'm solving here, albeit the current source is going to change in time. But at any given moment in time, I have a certain current, IL, and I can express I12 in terms of that. So let's use superposition. Use superposition. So first, I'm going to turn off Vs and have just IL. All right, so I12 is going to be equal to, when I have just IL flowing, that current source, and no Vs, I will have minus, because of the polarity or the direction of IL, minus IL times, and now I have current division between the 6 and 12 ohms, and it will be 6 ohms over 6 plus 12. So this is with Vs equal to 0, or off, okay? Then we're going to turn off the inductor current, and we'll have just Vs on. And now we have a voltage, well, no, we have a voltage divider, but that doesn't matter here. We have just current, we have a single loop, and we have a current I12 flowing that is just Vs over the sum of those two resistors. So it will be Vs over 6 plus 12. So this is when IL is equal to 0. Okay, so let me go to the next page and rewrite this. So we have I12 is equal to, let's see, that's going to be 6 times 1/3. So it'll be 2 times, minus 2 times IL. No, that's not right. I can't do the arithmetic. That is 6 times 1 over 1 plus 2. What am I missing here? Wow. Okay, that's 1/3. I don't know what I was thinking. Okay, minus 1/3 IL, and then plus, we found Vs, or we have Vs as 6 volts, so it's going to be 6 over 6 plus 12, and that will be 1/3 of an amp. And then let's suppose that I naught is equal to 0, okay, in this case. Then we would be able to write that IL of t, this is going back to our complete solution on the previous page, we have Vs over 9 ohms plus I naught, which is 0, minus Vs over 9 ohms times e to the minus t over tau, Vs being 6 volts. So we have 2/3. So we'll have 2/3 of an amp times 1 minus e to the minus t over tau. And this is for t greater than or equal to 0. Okay. So I just plugged in some numbers there. Once we defined I naught, we could get a numerical response. So this IL, what does this IL look like? Again, it's going to start at 0, and it's going to go up to 2/3 of an amp. Okay? Now finally we can say, therefore I12 of t is equal to minus 1/3 of 2/3 amps of 1 minus e to the minus t over tau plus 1/3 of an amp. Or otherwise put, we'd say it's 1/3 times, let's see, this is going to be 2/3, 1/3. Is that right? 1/3. Okay, minus 1/3. Minus 1/3 plus e to the minus t over tau. Okay, I think that's, let me just write this out. So we have 1/3 times 1, that's this guy here, 1/3 times 1 minus 2/3, is that right? Minus 2/3 plus e to the minus t over tau. So that's actually 1/3. Okay, so I got that wrong. This is plus 1/3. Okay? So what does that look like? At time 0, we're going to have, at time 0 we'll have 3, I really should rewrite this. Let me rewrite it this way. Let's say 1/9 times 3 1/9 plus 3 times e to the minus t over tau. Okay, I'll write it that way. So at time 0 we have 4/9. 4/9 of an amp And at time infinity, we have 1/9 of an amp. Okay, it's going to look like this. So what we have shown here is that you can take a circuit that looks a lot more complicated than just a single node pair or single loop circuit involving just an inductor and a resistor or capacitor and resistor. And by using network reduction, primarily Thevenin equivalent network, we were able to reduce the circuit to the familiar form that we've already studied. We could write the complete solution for the inductor current, and then we could go back to the original circuit and use the inductor current, or treat the inductor really like a current source, and then express whatever node voltage or branch current that we were being requested to solve for. And we could express that in terms of a weighted sum of independent sources, or source in this case Vs, and the energy states in the system, mainly in this case the current going through the inductor. Okay, I just looked over my math and I see that I have a mistake here, so let me correct this. When we went from this step to here, there is a 2/3 that I left out right here. This will become 1/3, and I can pull out, so let me have 2/3 over here, pull out the thirds, and I'm left with 2 right here. Okay, that's 1/9 times 1 plus 2 times e to the minus t over tau. And so at time 0, we have 1 plus 2, or 3/9, so 1/3. So this is not right. This is 1/3 of an amp. So it starts at 1/3 and it goes down to 1/9. And we can check this from looking at the circuit. So at time 0, the circuit that we have is, we have the 12 ohms, I12, and we have the 6 ohms, 6 volts, and then IL at this point is equal to 0. So we don't have to worry about IL. All we get is I12 is equal to 6 volts over 6 plus 12 ohms, which is 1/3 of an amp, which is exactly what we have here. Okay, and then so this is at time at t equals 0. So this is, I should say, this is IL at time 0 is equal to I naught, which is equal to 0 amps, as we have defined up here. So at time equal to infinity, then we would have, now we have an IL, and I'm going to actually draw it like as a current source. IL particular, we'd found before, was equal to what was that? Vs over 9 ohms, which is 6/9, or 2/3 of an amp. Okay, so now we can write I12 as the superposition, which we'd already written on the previous page. It was going to be, we found this previously using superposition. It's going to be minus IL, which is minus 2/3, times 6 over 6 plus 12, which is 1/3. 6 over 6 plus 12, 1/3, plus Vs, which is 6 volts, over 6 plus 12 ohms. Okay, so this will be minus 2/9, plus this will be 1/3, which will be minus 2/9 plus 3/9, and that will be 1/9 of an amp. And that's what we have. That's what we have right here. Okay. Okay, let's do one more example. This is a capacitor resistor example, and this one will have no independent sources, so just 3 resistors and a capacitor. R1, R2, R3. R1 is 30 ohms, R2 is 10 ohms, R3 is 2.5 ohms. The capacitance is 1 millifarad, and the voltage VC has initial voltage at time 0 of 100 volts. And the question is, find IR1 of T. Okay. So there's a couple ways you can do this. When I look at this circuit, without any external forcing, I know that the capacitor voltage is going to, the capacitor is going to discharge. The voltage will go from its initial 100 volts down to 0. And the manner in which it will discharge is simply is going to be exponential decay, and it's going to have a time constant that is going to be equal to the capacitance times the equivalent resistance that the capacitor sees. So one approach would be, let me treat the capacitor like a voltage source that's 100 volts. Let me find what the initial current is flowing through R1, and then my solution will simply be that initial current times my exponential decay. So let me show you this way, and then maybe we'll go back and solve it the way that we'd solved it previously. So here we go. We have 1. I'm going to find IR1 when VC is equal to 100 volts. Okay. Well, we're going to do that in 2 steps here. I'll label this IR3. Okay, and I want to see what the capacitor sees in terms of resistance when it looks into those 3 resistors. So it sees R3 plus R1 in parallel with R2. So that's 2.5 ohms plus the parallel of 30 and 10. So 30 and 10 is 300 divided by 30 plus 10, okay, or 40. So it's 3/4 times 10, or 7.5. And so 7.5 plus 2.5 is 10 ohms. Okay, so I can write that the total current here flowing IR3 is simply VC of 0, which is 100 volts, divided by 10 ohms, which is going to be 10 amps. Okay. Then I could write, secondly, I could write IR1 then is just the current division of IR3. So IR3 times 10 over 10 plus 30, so 1/4. 1/4 of IR3, and that will be equal to 2.5 amps. Okay, so therefore IR1 at time 0 is equal to 2.5 amps. Now at this point I can write the solution straight up. Because I know that at time 0 it's 2.5 amps flowing through there, and I know that the capacitor voltage is discharging in an exponential manner, all of the currents and all the voltages in the circuit are going to do the same. And I can say that because there's no external voltage or current sources. So in other words, when the capacitor voltage finally dries up and goes to 0, there will be no current IR1, there will be no voltage across R2 or whatnot. Okay, so therefore we can write IR1 of T is equal to IR1 at time 0 times e to the minus t over tau, where tau is equal to the R3 plus R1 in parallel with R2 times C. Okay, that's 10 ohms times 1 millifarad. So that's 10 milliseconds. Okay, so and this is valid for t greater than or equal to 0. And so IR1 will start at 2.5 amps, and it will just decay. This is IR1 of t, and we have a tau equal to 10 milliseconds. Now the other way to solve this, which is more work, would have been to find Vc of t, then find IR1 as equaling some function of Vc of t and Vc of t. All right. So Vc of t is going to be an easy find because we start out with some initial capacitor voltage VO, 100 volts, and then it's just going to exponentially decay. So it'll be e to the t minus tau, where tau is going to be the 10 milliseconds as we found before. Okay, so that's the first part. Then we simply need to write IR1 as a function of Vc. So IR1 is equal to, well, we can again find, we can use current division to express IR1 in terms of IR3. So it'll be 10 over 10 plus 30 times IR3, and IR3 is going to be equal to Vc over the total resistance that it sees, which is R3 plus R1 in parallel with R2. Okay, and then you could plug Vc in, and you could solve for IR1. So it's really doing the same thing, but it's in a little bit longer path to get there.